I'm very happy to have Siqi Liu telling us about the testing threshold in random geometric graphs.
So today I'll be talking about testing threshold in random geometric graphs, and this is based on joint work with Siddhant Mohanty, Salil Shram, and Elizabeth Yang, and Siddhant and Salil are here. Okay, so I think in flavor this will be quite different from the previous talk, but we'll see. Yeah, and maybe I should remark that if anything is not clear, maybe stop me and ask, because I'm not exactly sure what's everyone's background. So this is this workshop's topic's more like general than the previous two. Okay, so I'll just actually directly jump into a definition and maybe motivate a little bit later after we see the definition. So the object we're studying here is like a random geometric graphs. So this model is sampled in the following way. So specifically, there's a unit sphere in dimension D, and we denote it by SD minus 1. What we do is we sample endpoints on this unit sphere, and then the graph, the edges of the graph is sampled by connecting two points x and y if and only if their inner product is greater than some threshold tau. And tau of p is selected so that the marginal probability of an edge exists in this graph is exactly p. So yeah, and here we can see there could be more points being generated. And okay, I want to make two remarks here that will be related to later topics in the talk. So first is that this tau, this threshold, like basically this threshold that controls the correlation between the two vectors decreases as D increases. So it gets smaller and smaller as D increases. So in other words, like the dependency between the two between the two vectors are also getting smaller and smaller once D increases. Okay, another thing I want to comment on is that, okay, if we focus on a vertex, let's say y, the locus of all the points that can have an edge with y are precisely all the points that basically land in this sphere cap around y, because this is a collection of all points having inner product greater than tau with y. So that's the 2 points I want to point out here. Is that clear? Okay. So okay, and later in this talk, this model I just defined will be given this notation GLD NP. So it depends on the dimension of the sphere and also like probability P. The
limit if you take the limit of the dimension.
Oh, dimension to infinity. Now here we only consider D as a function of n.
Actually, the answer is yes. So you also say.
Okay. So okay, why are we interested in such a model? Well, such a model we've seen it's quite different from like let's say Erdős-Rényi model or even like deregular graph model, which are usually, I guess, the common model studied in many like average case problems and average case construction of things. So the key property that's different is this model introduces dependency between adjacent edges in the graph. Specifically, we see here that basically if we know that in the graph an edge exists between the vertex A and B and A and C, that means essentially B and C, as we commented before, will need to land in the sphere cap around A. And because of that, the probability of BC having an edge in between them is much higher than the probability that a random BC on the sphere will have an edge in between them. So this probability is much bigger than P, which is the marginal probability of an edge exists if they just come from two random points on the sphere. Okay, so what's good about this dependency? Well, okay, so two motivations. One is arguably it's a better approximation for real world network data and models than a model like Erdős-Rényi where every edge is independent of each other. So it can be maybe some of the algorithms that aim towards like real life applications should be tested on these kind of models instead of like the more classical ones. Yeah.
So do you get to see the D-1 dimensional representation of V1s?
Yeah, okay, good question. No, you don't get to see. Yeah. So the graph model really just samples the graph and all the information about the vectors are dropped. But that's a good point. Okay, and another thing which will be more of the topic of Salil's afternoon talk is that we see that this introduced some graph where locally the edge is more dense than globally. Like globally, like we have some average degree, but locally, if we just restrict our attention to the local neighborhood of A, they are like kind of more well connected than just some like a random subgraph induced by random vertices in the graph. Therefore, there's some intuition that it can be applied to construct a higher dimensional expanders, which are essentially expander graphs with well expanding neighborhoods. So, and this will be like Salil's talk in the afternoon. So this is a kind of a preview. Okay, so that motivates why we are looking at this model. And so now we want to see what's the first question we're interested in studying for this model. Well, now we know that actually as was asked before, like we're given this underlying geometric model, underlying geometric structure of this graph. But then when we're given the graph, really, we don't get to see the underlying geometric model. Yeah, that's in fact, okay. Glad that you like it. Oh, okay. Yeah, so this went away. Yeah. So yeah. The vertices went away. So okay, the vertices didn't went away, but the vectors went away. And now the question is, if we're only given a graph like this, how do we know whether it comes actually from a okay, this is unintentional, but okay, the point is, when we get rid of the underlying like vector structure, how are we able to tell like whether this actually comes from a model like the random geometric graph model we just mentioned, or it's actually coming from like an Erdős-Rényi model? So the first question is that of distinguishing whether a graph comes from like the Erdős-Rényi model or the random geometric model. So to be more precise, the two models we're considering are these. On the left, we have GMP, which is the Erdős-Rényi model, where we have like each edge in the graph is sampled with probability P uniformly, sorry, not uniformly, but independently. Okay, so no underlying geometric structure. And the one on the right is the model that we just mentioned, random geometric model, where we sample from a unit sphere, essentially. Okay, so so this problem has been studied before by Bubeck, Eldan, Rácz in 2016, and they were able to give a distinguishing algorithm in certain regime. So okay, maybe I should mention that this distinguishing problem, of course, depends on the certain parameters. Like in certain choices of D, the dimension of the sphere and P, this will be an easy to distinguish problem. However, in some other dimension, with some other choices of D and P, it will be hard. And okay, just to give some intuition, like when D is really large, like it can be imagined that as I mentioned at the very beginning, the first slides when we were defining the model, like when D is really large, the tau, the inner product dependency between two vertices from a random from a random geometric model. I mentioned that their underlying vector has a threshold that's much smaller. So it kind of decreases the dependency between vertices. And as a result, it's kind of making it closer to being like a Erdős-Rényi model, where the vertices are not, okay, where the edge, existence of one edge doesn't introduce that much dependency between vertices. Okay, this is a very, this is some intuition, but maybe what's easier to see is like, if we take the case when D is equal to 3, so we have a sphere in the 3 dimension. So it's essentially a 2D object, and every graph on it roughly need to be planar. So that's pretty different from Erdős-Rényi model, because a random graph from Erdős-Rényi model wouldn't be planar. Yeah.
Yeah, maybe you already said this, but was the tau chosen so that the edge density is the same in both?
Yes. exactly, yeah. Yeah, we compare them with the same edge density. Yeah, otherwise it would be quite easy to distinguish. Right, so
That's sort of interesting that here the edge density is used, right?
Oh yeah, it's yes, it's used here. But I think what's more important is they're trying to count number of triangles.
I mean, you can think about the situation where the edge density is like, you know, I mean, it makes sense that the edge density would help you because the denser it is, kind of the more information you're getting about the embedding, right? Like if P is 0, then you just see the empty graph. And there's no dimension at which you could hope to test these things, right? So.
Look, I guess if you know P ahead of time and just want to distinguish the things, then maybe you don't need to count it, right? Maybe only if you don't know P.
You do need to, yeah.
Yeah,
Maybe,
so in
but
this
the
case,
answer is
it's sort of like a variance reduction type thing.
Wait, sorry, here, do you know P or you don't know?
We know P. Yeah, P is known.
You can estimate P super well just by looking at the average degree in the graph. So that concentrates, I mean, that would be a pretty good estimate for P. So figuring out P is not a big deal.
So here's C1, C2, C3, they all depend on P.
They don't depend on N, actually, they depend on P. So this C1 is actually 1, C2 is negative P, and this C3 is P squared. Maybe, okay, I'll talk about this distinguishing algorithm maybe in a bit. It's actually maybe not. So this is essentially a algorithm that's trying to count a triangle in the following graph. Like instead of considering the graph where adjacency matrix is just 1 and 0, indicating whether there's an edge or not, we centered this matrix by actually put a minus P to all of the entries. And in this new weighted graph, you count the number of triangles. So that will give you basically the parameter as just said, where these structures are all structures in the original graph without subtracting that weight. So it's counting triangles in the center graph, essentially.
Is this indistinguishable?
Yes, they're like statistical. That's correct. Right. So okay. Right, yeah, so I was just trying to give some intuition about when D is small, this would be harder to distinguish, but of course, all of these statements, as Leo mentioned, all depends on P, because if P is too large or too small, it's going to be a clique or just a bunch of vertices, and we won't be able to distinguish. So with a reasonable choice of P, there is the sense of like, this graph would be closer to a Erdős-Rényi when D is larger and this farther away from it when D is smaller. So this result here by Bubeck, Eldan, Rácz is saying like in the distinguishing regime, they proved that for D smaller, much smaller. Okay, here in this talk, much smaller usually means you have a hidden polylog on the right hand side here. So when D is much smaller than HP cube N cube, where this is a binary entropy function of P, then we can use this algorithm to distinguish, counting the centered number of triangles to distinguish. And on the other hand, when D is much greater than N cube, this is statistically, the two distributions are statistically indistinguishable. And later on, Brennan, Bresler, Nagaraj have improved the indistinguishable bound from N cube to like D much greater than the min of these two. So N cube times binary entropy of P and HP cube times N to the 7 halves. So this essentially is making the bound much better, especially in the regime when P is like small. So to summarize, the two known results give us this graph. So if we have x-axis being P, the edge density, and the y-axis being the dimension we consider, the distinguishable regime is this regime here. So more specifically in the regime like when P is order of 1 over n, we have that we can distinguish when D is much smaller than log cube n. And we cannot distinguish when A is like, when D is greater than n to the 3 halves. So there's this gap. Yeah.
Just to confirm, the red region is statistically indistinguishable and the green region is also efficient algorithm.
Right. This is right. This is the efficient algorithm, and this is statistically indistinguishable. Okay. So okay, and in the denser regime, like essentially this gap is closed into the into the n cube. Yeah. When p is close to 1, I guess. Oh, I see what you mean. When p is close to 1, I do think it's n cube. I think it's close. No.
This diagram is only accurate if p is a half.
Oh.
On the other side, something similar kind of happens.
Oh, okay.
Yeah, I guess when p is closer to 1, it's like p less than half, but for like an
Complement graph.
Yeah, for complement graph, like connecting further away.
Okay, I see.
Probably the behavior should be similar.
But people didn't study it much, including us.
Okay, yeah, I should correct myself saying like this is up to p is smaller than 1/2. Yeah, right. I think yeah, symmetrically in the p greater than 1/2 regime, basically we're studying the complement graph of the Erdős-Rényi and the complement graph of this random geometric. So this work I'm going to talk about improve the indistinguishable side of things, and all the improvement are also statistically indistinguishability. So we showed that in general, when d is much greater than hp squared n cube, then then basically this in this regime random geometric is indistinguishable from Erdős-Rényi. And also specifically, we improved this result, this bound here, when p is on the order of 1/n, to that when d is much greater than log to the 36n, we have that this is statistically indistinguishable from Erdős-Rényi. So there is this gap between log cube and polylog in here. Yeah.
This whole chart should be red or green. Is it possible that they're statistically distinguishable, but there's no efficient algorithm in some regime?
Yeah, that's a good question. I would say I'm not really convinced by either side yet. I would say I don't have that much intuition. So I mean, there are certain barriers in the. Okay, so first I want to say like this log to the 36 is not heavily optimized. So it's possible that on this side it could be close. I'm not exactly sure, but in this regime in the middle, I think I'm more like uncertain. I don't know of a way, but at the same time, I also there could be a gap, you know, between maybe something is like just not efficiently distinguishable. I think that's possible too.
Also, you should point out, I mean, this drawing, it's not really to scale like the diagram.
Oh, yeah. These lines are not supposed to be. That's true.
On the X.
Yeah. These are all polynomials.
No, in particular, the x-axis is okay. So suppose you were asking like, what is the evidence for should like whole like wide area be filled in with red? From the way that this drawing is drawn, it kind of makes it look like it probably should be all filled in with red. But like what's really happening is that actually this alpha over n region is like, you know, like the x-axis is super not to scale, right? So that's actually like a super thin line. And so we're like, I mean, the red line extends all the way.
Yeah. So yeah, right. So this entire thing is the order 1/n regime, but supposedly this should be like in a tiny slice at the very beginning. Oh yeah, so this entire improvement is only for order 1/n, not up to not up to something much bigger. Yeah, maybe there should be like dotted lines next time. Okay, so right, so okay, there's some gap as already pointed out by the audience. And yeah, and this could be something that one could look into, like as to whether there should be no like there should be like nothing, no inefficient algorithm that distinguish, or it could be like actually some other things other than trying to count triangle really distinguishes these things better. We did try, yeah.
I have a question. So the distinguishing algorithms. So how sensitive it is to really be working on the geometric graph? Let's say take a geometric graph, and then you add a bit of randomness to it. Like you maybe delete a few edges randomly or add a few edges randomly. So will it still work?
Distinguishing algorithm? Yeah, I think so. Yeah, it's should be, this is pretty robust. This yeah, we've also tried, I think, a couple other, I guess, also efficient distinguishing algorithm, but none of them really beats triangle, this center triangle counting. So yeah, but I think inefficient one, I don't remember trying. Okay, so next thing I want to do in the talk is really to prove this main lemma, like or give a proof sketch of it. So okay, it could be a bit ambitious, but we'll see how much we can get. So I'm only proving the here the statement is only for the p is on the order of 1 over n case. However, I want to say that halfway through the proof, we'll obtain the first result, which is for the general choice of p, but a worst bound that I showed in the previous slide. Like this one will be obtained halfway through. And later on, we'll optimize for specific choice, this sparse p regime. Okay. Yeah.
So also imagine trying to patch the Erdős-Rényi graphs by like adding triangles randomly and stuff to fool whatever the distinguishers are. So
Yeah.
is that like an interesting thing to do, like, or yeah.
Yeah, I guess that's true. You can try to fool it by adding triangles. That would definitely fool that algorithm. But maybe there could be some, okay, even that I'm not exactly sure because it also involves counting like, you know, because that the counter count like center triangles. So you got to add them in the roughly even way in some sense. Actually, maybe that would work, I would say. I'm not very sure. But I can imagine maybe some more intricate way, some smarter way of adding triangles could make it work.
Triangles means you only look at triangles in the middle.
Oh no, it means like even for the basically subtract p, you add a minus p to all the edge weights. So now it becomes edge weight either 1 minus p or negative p, and then you count triangles in this complete graph essentially.
But you do expect the links to look very different in the two in one.
Yes.
Depending on the
So, but yeah, that's an interesting question. Okay, and the essential way to prove this statement, we just want to show that the TV distance between the two random graph distributions are little of 1. And okay, to prove this, maybe I'll introduce a more sequential way of viewing the sampling process from these two models. Okay, so I guess one can imagine sampling the model like by adding 1 vertex at each time. So at time gt, at time step t, we have gt, where it's a subgraph induced by basically the first t vertices in the graph 1 through t. And given this graph, one can construct a gt plus 1 by having this vertex and sample their neighborhood, sample the neighbors of t plus 1 inside the first t vertices. This may sound like tautology, but this will make more sense once we actually start to work on the proof. So the key distribution that I want to point out here is this distribution neighborhood of a vertex. So neighborhood of a vertex t plus 1 in the Erdős-Rényi model, we know it's just a binomial distribution roughly. Well, exactly. And the neighborhood of a t plus 1's vertex in the random geometric graph, however, will be much more complicated. It will depend on GT itself, right? We can imagine. Okay, so right, so okay, I think I already mentioned this part. So Let's just review a little bit how this how this distribution is defined. So once we're given a graph GT, what we do is we can consider what are the vertices V1 through VT on the random sphere that generates this graph. So this is a distribution of all eligible, like all the vertices, all choices of vectors on the sphere that generates this GT. Okay, and once we get a bunch of vectors for the first T vertices, then we can sample this T+1's vertex randomly, and then look at what's the distribution of its neighbors. Okay, so this is a more complicated distribution to describe. And okay, so essentially to prove the statement of TV distance being very small, it boils down to just prove like this two distribution I just introduced, the neighborhood distribution of Tth vertex, T+1th vertex. They're very close to each other. Their ratio need to be within 1 ± (1) over square root n. This is the goal we have. Okay, of course, this is with high probability over choices of S and with high probability over choices of GT. Okay, so these are all like probabilistic statement, but essentially this is a real thing we actually want to prove. And after that, there's some standard arguments that can bring this bound just into this TV bound. Is everyone clear about what this ratio means?
Is there any addition why you only need square root n?
Why you only need square root n? Okay. I want to say I'm not sure at this point. Yeah, I want to think there's some like. Okay, let me not try to guess. I will give you an answer afterwards. Okay.
So here, this S is it's for all S or?
Okay, with high probability over S, and the probability you can think about the probability over
From GNP.
yeah.
Like you can think about, it's not, this isn't really how the argument goes, but you can think about an argument that goes like this. So you're trying to couple the formation of GNP and the geometric graph. And if you can couple the distribution over the neighborhoods of each vertex that you get in the sequence, then you can succeed. So then, okay, there's some quantitative reasons why we need the coupling to be this good. But right, this is what you're shooting for. You're shooting for such a good coupling between the distribution over neighborhoods in the two graphs.
Yeah, but you have n steps, that's why it's.
You have an n steps, so that's why like the 1 over root n shows up. Why is it 1 over root n, not 1 over n? Let's not try to figure that out.
It seems to me it should be like 1 over n squared, right? Because Pinsko goes the other way. But never mind, we don't need to go.
Okay, let's not go into it now. Yeah. I mean, okay, like here's a thing that I can say that's very irresponsible, but I can say that anyway, right? So we're doing n steps, right? And the error, it's like you could, if you think about it as a stochastic error, then maybe you only accumulate like root n, like over the n steps, maybe you only accumulate like a root n factor over this error.
Oh, okay.
That would be the guess, but yeah, yeah, but I think that's probably the actual thing. Okay, so right. So okay, so now we have this ratio. We want to basically bound this ratio, so it's here. Okay, so to understand this ratio, we need to understand better what's the probability in the numerator. It really is. What's the probability of having a neighbor, basically having exactly the neighbor set being S in the random geometric model means? So essentially we can imagine, okay, let's say that we already have this distribution, like condition on GT, we already have a bunch of vertices, or sorry, a bunch of points on the sphere corresponding to the first T vertices. And around each of them, I draw a sphere cap. The sphere cap is what we had at the very beginning. Basically, everything in the sphere cap is all the possible points that could have a edge with the center here. Okay, so once we have this graph on the first T vertices, then basically each of these splinter, like each of these small shapes here with a different color in this graph, they would correspond to a set S. Okay, so what does that mean? Basically a set S is, for example, this, let's say this shape here correspond to just this vertex because it's only in the sphere cap of this vertex and outside the sphere cap around all the other vertices. So essentially, given a set, the area or the splinter corresponding to the set S is intersection of all the sphere caps around centered around some vertex VI where I is in S, and also intersecting with the fact that it's outside all the other caps that's not inside S. For vertices that's not inside S. Explain a bit more, like yeah, because this is a pretty important concept we'll be using later. So basically, if for each of the, okay, if I landing a different color here, I will have a different set of neighbors. Does that make sense? Right? And what set of neighbors am I really in depends on, like, okay, in this color, in whose like a sphere cap I'm actually landing in. So the splinter, according to S, need to be the areas that lands in all the sphere caps that with centers inside S and not in the sphere caps. Then outside the sphere caps, where with centers outside S. Okay, okay, cool. All right, yeah, okay, so this probability then can be essentially be written as the area of this, the fractional area of this splinters. It's actually expectation under this distribution, where this distribution we're free to choose V1 through Vt as long as they generate the graph GT. Okay, so yeah, this is interpretation of this probability. It's expectation of area of a shape. Okay, so essentially we know that, okay, one thing we know really is that maybe this is not the right order, but one thing we know is that in expectation, okay, yeah, let's not say that. Okay, first attempt to prove that these two are very close. We're trying to kind of make life easier for us by, instead of thinking about this probability, this expectation concentrate, this quantity concentrate in this conditional expectation, we make life easier for ourselves by looking at removing this conditional and trying to show that probability of S concentrate around this expectation where we remove this condition. So we just randomly sample V1 through Vt, don't care about what graph it generates. And we want to see if already in that case, so supposedly that's a harder case. It's harder to prove concentration on an unconditioned distribution. Well, okay, condition is making it in a reasonable way. So usually it should make it easier to prove concentration. Here it's making it a bit hard for us because it's a bit hard to imagine like what are the distributions over V1 through Vt when we require that they have to generate this GT. So we make the simplification here first by thinking about just this distribution, removing this conditional part. Okay. All right, then, and the reason it's first attempt because it actually failed somewhere, but it will already give us some non-trivial improvement. Okay, so when we think about just the distribution over the first T vertices, and we're imagining like what's the probability of S in this distribution. Okay, sorry, I should have removed this conditional here. Then it's roughly like you have a bunch of sphere caps and you're looking at how this splinter evolves through time steps. What do I mean by that? If we have the example being like S is equal to 1 and 2 and S complement equal to 3. Okay, in the first step, when we sample a vertex, we have a sphere cap. So the splinter hasn't appeared yet in some sense. But in the next time step, we have 2. We sample the V2 at some point. Now the splinter we look at we're interested in that eventually generates splinter of S is this intersection between 1 and 2. And in the third step, when we sample S, because, when we sample vertex V3, because 3 is not in S, so we care about its intersection with 3 complement. So this is the shape eventually we care about, which is splinter S. So there is some evolution, like essentially these splinters are generated by the intersection of a bunch of caps and anti-caps. So we want to prove that this probability, the area of the splinter concentrates. And how are we doing this? We're looking at a more, yeah, that's right. This will be here actually. So yeah, as Lil suggested, we'll consider actually a slightly more general question, where we just are given an arbitrary shape, essentially arbitrary shape L over the sphere. And now we ask the question like, what's the area of this shape which is L intersect the cap of W, where W is a randomly sampled points on the sphere. Okay, so this is a distribution. So we want to know the concentration of the distribution. And of course, we care about what's the expectation. Well, actually in expectation, the intersection between L and the random sphere cap of fractional area, let's say P, is equal to P times area of L. This is by, let's say, linearity of expectation.
So what is L supposed to be in the previous? It's the
it's whatever L is an existing intersection of caps and anti-caps, and now we're intersecting with with one more cap or anti-cap. So that's what roughly L is, or that's the actual L that we applied the theorem to. But the theorem really applies to more general L. As you see this weird shape here, this could also apply.
So here you are arguing about a worst case S throughout, but actually you only care about sort of the typical S that shows up, right?
Yeah, I would say actually this is not really a worst case S that I'm considering here. I think all of these statements I kind of drop with high probability type of thing. But the difference here though is very important, is that I'm choosing V1 through VT without restricting that they have to generate a certain graph. I think that's a relaxation actually made in this attempt. Because as you can see, like at every step, I'm just sampling W randomly without requiring that W has to come from a certain area. Yeah, if I restricted that, it would be actually faithful to the actual expectation, actual probability I want to set. So this is the okay. So this is the expectation of this quantity P times area of L. That's actually really good for us because actually adding a P multiplier in the beginning sounds really like what's happening in Erdős-Rényi models and stuff. So now we really want to know if it actually concentrates well around this expectation. Well, without really talking about how to prove this, I would just give the statement here. And this is through an application of Talleyrand's T2 inequality, use some optimal transport result. So the theorem just says that, okay, if given arbitrary L and a randomly sampled W, the area actually is concentrated well around P with an error of 1 plus minus okay, let's say just the square root 1 over D. Let's not worry too much about this thing here, just polylog, some polylog factor. And also we have a similar result when L is intersected with an anti-cap, so complement of a cap, which also concentrates even better, essentially. Okay, so this is what we get, but is this good enough for us? So that theorem, previous theorem, will actually give us something like the ratio we care about is within 1 plus minus O tilde of 1 over square root D. That's a bound we get. Recall that our target, like what we need to get, is little 1 over square root n. So there is, okay, it depends on your choice of D. So if D is much greater than n polylog n, then actually these two are the same, and we're already good. And actually this, if you plug in this choice of D, this is exactly the first result, weaker result that applies for more general P that we had. Okay, so this already, basically that concentration, this concentration already get us something, some improvement from in comparison to the previous result. But we want to do a bit better for like when for D that's smaller. Like our target really, like in the theorem, is that we want to do something for D greater or equal to polylog n without this m factor. So we need to do better. Where did the slack come from? The slack really come from the fact that we studied, we didn't really think about this part. We didn't think about, oh, we have to make sure that V1 through VT actually comes from, actually have to generate a specific G. We can imagine once they have to generate specific G, maybe the graph structure is more rigid. You have to have like certain relationship between the first T vertices, and therefore that makes like this probability more concentrated because the shapes are roughly like structured, like rigid. You cannot change them too much. So the key thing is really to study this conditional distribution instead of like the unconditioned distribution. Okay, so in the rest of the talk, I will, okay, we still have time to go through this, like what's changed in this argument when we have to condition on GT. So, but maybe before that, let me say, like to make the presentation easier, I secretly relaxed this ratio we want to get. Before I said the ratio we want to get is really like when the neighborhood is exactly equal to S, the ratio between the two different models. Here I would make the relaxation, just say, okay, I'm just going to look at the probability that neighborhood contain a subset S. And it suffices for us to get something, to get the same ratio for this containment relationship actually. And I will not really say why, but yeah, it's a bit more complicated than just inclusion exclusion. Okay, so yeah, let's this is just quickly recall that how this distribution is defined. So we have a graph, and we have to sample a random set of vertices that actually vectors that actually generate this graph. And after that, we look at the all possible neighborhood of a randomly sampled T+1 vertex. It would be good. Okay, so what's ideal for us? Well, what's ideal for us is it would be really nice if if even conditioned on this G less or equal to T, every single vertex in every single vector for vertices inside the set S that we chose is going to be IID and uniform over the sphere. If this really holds, then actually we could see that the probability of a random edge a random vertex having S being contained in its neighborhood is P to the S. Again, this is because of the expectation calculation that I omitted here. So next what we'll show is that with high probability over choice of GT and also with choice over S, this will actually be true. That we will actually have all these vertices, all these vectors inside the set S being roughly independent and uniform over the sphere. Okay, so this may sound a bit strange, like why could we get that? Well, we actually crucially use the fact that this is a sparse graph. So we're really now in the regime where P is order of 1 over n. And let's see why. So consider this following constraint satisfaction problem on this graph GT. Now we impose the edge constraint and non-edge constraint. So the variables are essentially all the vectors we assign to the vertices 1 through T. And the constraint is that okay, all the vertices with edges need to have like large inner product, and all the non-edges should have small inner product. So the solution to this CSP is essentially the set of all possible assignment with non-zero probability in this conditional distribution, because they are able to generate the graph GT. Is this clear? Like I'm just defining a CSP here. Nothing really happened. But the CSP kind of give a description of this distribution. Uniform distribution over the satisfying assignments of this CSP is essentially this distribution here. I guess I omitted one thing, which is all the VIs need to be on the unit sphere. Okay. Okay, once we have this, we want to analyze a marginal distribution of a small set of VIs inside this satisfying distribution. Before doing that, we will first make another simplification, which is we drop the non-edge constraints. It turns out this doesn't influence the marginal distribution of small sets too much. So we'll do that. It doesn't hurt the intuition of the approach either. So yeah. Okay. Now we actually want to look at this solution distribution. So this is a very nice picture. So okay, so we talk about, this is the regime we care about is really the regime of PO on the order 1/n. So why that? Okay, now here's the real reason. The sparse regime will guarantee two things. First is, so the GT are sparse, so they're locally tree-like, which is drawn like this. Like this entire graph is GT. And second, if we look at local neighborhoods of S with true sum L and look at the L neighborhood of S, they'll all be tree-like, and also they'll with high probability be disjoint from each other. So this is a high probability statement that holds specifically for the sparse regime. So we can have a graph that looks like this graph here on the left. Okay, so once we have this, we consider the following thing. We consider any assignment, like any typical, well, kind of nice assignment to all the vertices in the middle bulk here. So we fixed all their assignment. And look at after we've conditioned on these assignment, what are the conditional distribution over all these S, the choice of S, basically the vector assigned to S, to all the vertices in S. Okay, so first the claim is that they're independent in this conditional distribution because we fixed everything in the middle here. So after we fix everything in the middle, these are conditionally independent from each other, especially when we remove the non-edge constraint. Maybe I should pause here. Because now essentially we're only left with edge constraints. So once all the roots of a tree is fixed, like S really depends, this choice here, for example, only depends on the assignment of these vertices, not anything else here, because we dropped the non-edge constraint. And they're independent from each other also just because their root vertices are also disjoint sets.
Depends on what L is, right?
Depends on what L, okay, sure, it depends, yeah, it depends on L. And we'll choose L to be large, like log n over log n neighborhood. Yep.
You have independence, you don't have the independence.
Yeah, technically not, but in spirit, yes, I think. Okay. Yeah, of course we wouldn't really get uniform distribution because to generate GT, this is definitely not going to.
No, I mean I'm just saying like the claim that you've written on the slide. I think independence isn't that difficult to see because it's the usual reason why I put up like a graphical model and you condition on some stuff.
Right.
But uniformity is like not at all easy to see.
Right. Yeah, no. Actually, I'm going to explain uniformity. Here, I just want to explain like independence. Right, independence, I guess, okay. Now I see, okay. Yeah, okay. So this is independent and uniformity, I'm going to explain it next. So essentially uniformity, we just need to single out one thing and prove uniformity. And then independence will tell us they're all like kind of simultaneously uniform. Okay, so as mentioned before, like the assignment of this root vertex is what we actually care about. And now we have all the leaf vertex assignment being fixed. So we now just need to know, like, once the leaf vertices are fixed, what's the distribution over the root vertex assignment? We want to claim it's uniform. And we'll show intuition on a very simple tree, which is a path. Okay, so we want to know the distribution over V root given V leaf. Let's say this green dot is the leaf vertex. So this is this point on the sphere. And now this blue circle around it is the support of its parent, right? So its parent is some vertex that actually connects with the green thing, which means that the distribution of its parent is really like a uniform distribution over the sphere cap around this green vertex. So yeah, so I will use notation Fy for the PDF for Vy. So in general, when we know the PDF of a vertex X, and now we want to infer from it the PDF of its parents in this tree. The procedure of doing that is really just, this distribution is defined by sampling a random point from Fx and then walk to a random vector around a cap in W. And this will generate a new distribution, which is its parent's distribution. Clear, it's like in the most degenerate case where Fx is just a point mass here on the green vertex, then its parent will be a uniform distribution around over the sphere cap around it. And more generally, you can always do this for every point in the support. And this process that's being described here gives rise to a Markov operator P, which essentially, walks from every point to a random vector, to a random points around its sphere cap. So we can write, in this way, we can write the parent PDF is really equal to applying this Markov operator to the child's PDF. So more generally, like the roots distribution is really applying this PL times to the leaf distribution. Okay. And what's left to be shown, like we want to say that this is uniform. So what's left to be shown is that really like this is a contracting operator. It contracts the distance between a distribution with the uniform stationary distribution. The uniform distribution over the sphere is the stationary distribution of this Markov operator. So we just want to show that this P operator contracts the TV distance to the stationary distribution. And yeah, also using like a similar optimal transport result, we can show that really by applying P to F, you actually contract the TV distance by a factor of 1 over square root D. And with our choice of L, then this can be made into little of 1 over square root N. So essentially, the root vertex distribution is really close to uniform as a result. That's really accelerated, but if anything is unclear.
Show it more generally for graphical forests.
Yeah, more generally for a tree, for general tree, it will be similar, but the analysis is more tricky just because, you might have multiple children to get to its parent, then there's some convolution going on. Yeah.
Same mix it up.
Yeah. Okay. So, once we're able to get this uniformity here, we get this uniformity of VIs inside S, then we'll be able to prove this ratio, like this containment probability ratio is within 1 plus minus little of 1 over square root N. And from that, we'll be able to get back to the theorem statement that we want, which is that TV distance is little of 1 between the two models. And yeah, this will be it. Was there?
How sensitive are the proofs to the fact that you're on the sphere? If I did it on a d-dimensional torus or something, would anything need to be changed, or would the proofs be changed, stay the same?
Good question. Okay, I think, so I'm not sure, like, is there an optimal transport result on the torus? Because we heavily use the one that's actually for the sphere. Yeah, so I think that part is really customized to sphere. But if something similar, like you can, similar results hold for a manifold that basically balance the optimal transport, the W2 distance with, let's say, KL divergence between two distributions, then I think it should, many of things should transport.
I think different geometries also behave pretty differently. Like, it's not even clear that triangle counts are the right test statistic to distinguish on the torus. Like,
Use whatever method you want.
okay, but then I mean, so like, I'm just saying, you know, like the fact that the test statistic is so different means that maybe like the proof of indistinguishability would also be pretty different.
Are you sure saying?
Let's stop on one.
This is a note for the questions that sent the KM.